how do you see black holes in your mind's eye? So I'm asking, the objects themselves, if I understand correctly, are of extremely, extremely large mass, but essentially infinitesimal size at their core. And of course, there's no light within the event horizon of a black hole to perceive. So do you see in your mind's eye like something point-like and kind of seething, or something massive and rippling that might correspond to the event horizon, like warping light all around it? Or what is it that you're envisioning when you think about black holes?
Okay, so I'll walk you through my imagination approaching a supermassive black hole. So the first thing that I think everyone should know about supermassive black holes is that, like, black holes are like dogs. The small ones are like really tiny and yappy and can bite you and hurt you. So if you get close to a small black hole that's a few times the mass of the sun, if you get close to the event horizon, it'll start to spaghettify you, right? And like shred you, because there's something called the tidal disruption radius. And that's where this spaghettification, which is actually a technical term, happens, right? With a supermassive black hole, that spaghettification happens inside the event horizon. So you could actually be, in your spacesuit, taking a walk outside and accidentally cross the event horizon of this black hole and still be in one piece, right? So like the big ones are nice and kind of fluffy, and you don't really have to worry about them. And the small ones are where you'll get like instantly, well, not instantly, but at the event horizon, you get spaghettified. And so it would be very difficult for you as an observer to cross through and actually like look inside and see what's happening. It doesn't mean that you can ever come back and tell anyone what you see, but it means that at least you could cross over into the black hole inside the event horizon and actually look around for a little bit and see what's happening before you eventually die.
Is it because I don't know what the technical word would be, but the gradient or the shift of the gravitational force, it sort of gets stronger much more quickly because of the
I think your intuition is right. It's the curvature.
Okay. Exactly. Okay.
Yeah, exactly. So it's the curvature of space-time that's, supermassive black holes are so big that you have a more gentle gradient at
Perfect.
first,
Yeah.
right? Whereas with the smaller ones, you're like, bam, right into the black hole. So yeah, that's exactly right. It's this curvature argument. So, but of course, this is all assuming that there's nothing else around the black hole. In reality, supermassive black holes are in the centers of massive galaxies, and there's lots of stuff happening there. So these supermassive black holes can have disks of material around them that are superheated. And so if you've seen the movie Interstellar, you've probably seen what's become, I think, this iconic image of a supermassive black hole that has this accretion disk around it, the eyebrow on top of it. So fun fact about that eyebrow is actually the back of the accretion disk. So if you imagine like my head is the black hole and the accretion disk is around it, because there's so much curvature in the space-time, it allows you to see behind.
It's gravitational lensing.
Exactly. It's showing you what's behind the black hole viewed at a certain angle with the camera. And so that's a cool fun fact.
Yeah, and those, I think, gravitational lensing, again, you can correct me if I'm wrong, that was a crucial experiment for supporting some of Einstein's theories, that you could look at a star. I don't know if it was originally performed with the black hole or with
the sun.
Okay, yeah, the sun. You could see stars that were behind the sun, but because the light it travels this, I don't know if I'm using the word geodesic correctly, but this path around the sun.
Yeah, that's right. So it happened during a solar eclipse, because that's the only time where you can see the stars that are close to the sun, right? And so if the sun is being eclipsed, then you can actually start to see the fainter light. And so you can see, where the stars should be, and you measure where they actually are. And then that light deflection tells you that actually, yes, the sun is curving space-time around it, and the position that you see of the stars is slightly deflected because of that curvature. So back to the black hole. So now you're, close to the supermassive black hole, and let's just imagine that you're Mario and you are in one of your like, indestructible suits where like nothing can harm you. You've had like one of those star power up things, right? And you're
Okay. I was wondering where Mario was coming into
exactly
this.
like, so let's just pretend that it doesn't matter that there's X-rays coming at you, ultraviolet rays, that it's hot, that, basically if you look at it, you'll die. Just ignore all of that. And now you can cross into the event horizon of the black hole. What's inside is really anyone's guess. But formally, what we do know, just by looking at the map, is that the space and time coordinates flip. It's really hard to understand what that means in a physical sense, right? But it's true. It happens. And also, like, if you're crossing through, like, your own clock and your brain and your perception of reality keeps going, like, normally. But if someone were watching you cross into this black hole, they would never actually see you disappear into it. You would just kind of get slower and slower and slower as you got closer to the event horizon, but they would never actually see you cross through it. So for them, for this external observer watching you, like, you never cross. But you, as the explorer, you just go through and you just keep going on and like looking around you. So it's really incredible. This is all relativity, right? Everything just depends on your point of view, and observers can, perceive things happening at different times, and space and time and gravity is all really intrinsically intertwined in this. And so inside the black hole, what I imagine you'll see is, formally you can't see the singularity because the singularity you can only see it when you hit it. But imagine that there's some sort of core, right? It's probably some quark gluon plasma, some sort of very exotic material. And that can definitely have light that comes out of it. That's entirely possible, that inside the event horizon of a black hole, there's light that's traveling and it's coming out of this central object, however you describe it, but like water coming out of a water fountain where the light can come out and it goes up to the event horizon, but then falls back down, right? Because the light can't escape. Or maybe some of it kind of goes around and traces a line around. So the light can really be traveling all over the inside of the black hole. So it could actually look like the 4th of July on the inside of one of these supermassive black holes. The disappointing part is that, according to what we know right now, we will never be able to know or to tell anyone what happens. Like, even if you and I decide to take a picnic inside the event horizon of a supermassive black hole, we can never tell anyone what we see because we can't get information back out of the black hole.